The GTAC series is divided into two sections. The 10 modules of the GTAC1 section provide the language and foundation you will need to understand the basics of air conditioning. The 9 modules of GTAC2 contain more advanced material on mechanical air conditioning systems. To ensure your understanding of the material, answer the skills check questions scattered throughout each module. Check with your instructor if you need additional help. By reviewing the student skills inventory at the end of this module, mastering the material, and checking your knowledge through the skills checks, you will be using the building block learning process effectively. It is important to understand the material in each module before moving on to the next building module. This 8th module, called Metering Devices, will continue to build your knowledge about the mechanical refrigeration system and its components. Our purpose is to review the placement and function of the metering device within the refrigeration system and to describe the types in use today. We also shall discuss how the metering device adapts to a changing load. The liquid metering device is located between the condenser outlet and the evaporator inlet. High-pressure, high-temperature liquid refrigerant from the condenser enters the metering device. The refrigerant leaves the metering device as a low-pressure, low-temperature mixture of liquid and vapor. The liquid metering device, regardless of type, is designed to provide two important functions in the mechanical refrigeration system. First, it allows the liquid refrigerant to flow into the evaporator at a rate that matches the rate at which the evaporator boils liquid refrigerant into vapor. Secondly, it provides a pressure drop, separating the high side of the system from the low side. This pressure difference lets the refrigerant in the evaporator boil at a low enough temperature to absorb heat into the system from the area or substance being cooled. It also lets the refrigerant in the condenser condense at a temperature high enough to reject heat from the system to the outdoor air. In the modules entitled Compressors, Condensers, and Evaporators, we showed how the functions of each of those components look when plotted on the pH diagram at normal design conditions. Here we used the same approach for the metering device. As the refrigerant leaves the condenser, it enters the metering device at point 4 as a high-pressure, high-temperature, subcooled liquid. 10 to 15 degrees of subcooling is typical. It exits the metering device at point 1 as a low-pressure, low-temperature mixture of saturated liquid and saturated vapor. As the refrigerant flows through the metering device, it drops rapidly in pressure, as shown at points 4 and 1. Unlike the refrigerant's passage through the compressor, condenser, and evaporator, there is no change in the enthalpy of the refrigerant as it moves through the metering device. The straight vertical line connecting points 4 and 1 in the diagram falls on the same enthalpy line. This happens because, unlike the other components, the flow of refrigerant through the metering device is almost instantaneous. There is so little time for heat to be exchanged between the refrigerant in the metering device and the air surrounding the device that it can be ignored. For all practical purposes, we could say that the metering device is purely a pressure drop device. The change in saturation temperature of the refrigerant is the result of the pressure drop. The refrigerant changes condition from a subcooled liquid to a saturated liquid-vapor mixture because of the pressure and saturation temperature drop caused by the metering device. The saturation temperature on the high side of the metering device is determined by the condenser pressure, while on the low side, it's determined by the evaporator pressure. In order for the 105° Fahrenheit liquid refrigerant at point 4 to drop to the 40° Fahrenheit saturation temperature at point 1, heat must be removed from the liquid at point 4. Since the metering process shows no change in enthalpy, the heat has not been rejected outside the refrigerant. Instead, a portion of the heat in the refrigerant is transformed from sensible to latent heat. This is how it works. Some of the liquid refrigerant boils into vapor at the saturation temperature and becomes bubbles of flash gas. Just enough sensible heat is rejected by the liquid refrigerant in the process of producing flash gas that the refrigerant drops down to a saturation temperature that matches the pressure in the evaporator. Likewise, just enough latent heat is absorbed by the refrigerant in producing flash gas to produce a similar saturation temperature drop. A sensible heat loss from the liquid is matched by a latent heat gain of equal quantity by the vapor. At the entry to the evaporator, a mixture of 80% saturated liquid and 20% saturated vapor or flash gas is about normal for comfort air-conditioned systems. Here are some typical changes the metering device will cause in R22 in a system using an air-cooled condenser. These data assume an outside temperature of 95 degrees Fahrenheit. Now we'll discuss 8 types of metering devices. They are divided into 2 general categories: those which have a fixed, non-adjustable opening or orifice, and those where the orifice can be adjusted to accommodate the cooling load on the system. The capillary tube is the simplest of all metering devices. It is a fixed length of small diameter copper tubing, usually with an inside diameter of 1/16 to 1/8 of an inch. It is normally located just ahead of the evaporator, as shown here. Because of its high frictional resistance to flow, it restricts or meters the flow of liquid refrigerant from the condenser to the evaporator. The greater in length or smaller in diameter the cap tube is, the greater the pressure drop it creates. It is often coiled to conserve space and to protect the capillary tube from damage. All the liquid leaving the condenser must flow through the capillary tube before entering the evaporator. Therefore, its diameter and length must be selected so that at design load conditions, the flow capacity of the tube is just the same as the pumping capacity of the compressor. If the capillary tube is too long, or its diameter too small, or both, the evaporator will become starved for refrigerant, and too much liquid refrigerant will build up in the condenser. The combined effect will cause the system to operate at too high a head pressure and with inadequate cooling capacity. In addition, the operating cost will increase. These same symptoms occur when a properly sized capillary tube is partially plugged with debris. If the capillary tube is too short, or its diameter too large, or both, the evaporator will be overfed. This may allow liquid slugging at the compressor, and too little liquid refrigerant will be built up in the condenser. The combined result will cause the system to operate at too low a head pressure and perhaps too high a suction pressure. These conditions result in reduced system cooling capacity. Because its design is critical, the cap tube is usually custom designed and installed at the factory rather than in the field. It's best suited to close-coupled split systems or packaged systems. When it's properly selected and applied, the capillary tube compensates for load changes over a reasonable range of operating conditions. It's poorly suited to jobs that have large changes in cooling load. As a result, it's most often used on equipment with 3 tons or less of cooling capacity, where there are fairly constant loads. Household refrigerators and freezers, room air conditioners, and small central air conditioners and heat pumps are examples of its use. Since the capillary tube is very small in diameter, it is easily plugged by debris that circulates with the refrigerant. For this reason, a liquid line filter normally is installed upstream of the capillary tube. Unlike modulating types of metering devices, the capillary tube has no means of stopping the flow of liquid refrigerant to the evaporator during the off cycle. When the compressor shuts off, the pressures of the high and low sides equalize by flowing through the open capillary tube. Any liquid left in the condenser at the time of cycling off tends to accumulate in the evaporator and remains there until the compressor turns back on. This liquid has the potential to be drawn into the compressor at startup. This action causes slugging, especially if the system is overcharged. In some cases, the liquid can migrate to the compressor crankcase at shutdown. There, it mixes with the oil. This will cause foaming and poor lubrication when the compressor starts again. Therefore, a suction line accumulator is sometimes installed in systems that use a cap tube. The accumulator captures liquid refrigerant and returns it to the system as a vapor. Additionally, special care is given in charging systems that make use of a capillary tube. An alternative design to the capillary tube is a fixed orifice. It accomplishes the same thing as the capillary tube, but in a compact and rugged assembly. A major advantage of the fixed orifice over a capillary tube on heat pumps is that the orifice can be built into a check valve that allows reverse flow with less piping and parts than are required for a capillary tube. It is like the cap tube in three major ways. 1. It requires careful selection to match the system in which it is installed. 2. It demands accurate system charging procedures. 3. It permits refrigerant migration into the evaporator and even into the compressor crankcase during the off cycle. Therefore, the same precautions, recommended accessories, and troubleshooting guidelines apply to the fixed orifice as to the capillary tube. Like the capillary tube, the fixed orifice is factory selected for its application. In split systems where the outdoor unit and air handling device may be purchased separately, the correct piston must be installed in the metering device during installation. The piston shipped with the outdoor unit matches the unit's capacity. A system using a capillary tube or fixed orifice metering device operates at maximum efficiency only at the design operating conditions for which that device was selected. These devices have no mechanical means for adjusting to load changes in the system. At all conditions other than design conditions, the system's efficiency is therefore not the best possible. Realistically, however, these devices operate just fine over a normal range of operating conditions. It is when loads change rapidly or widely, or when extremely low loads occur, that problems show up. One of the best ways to avoid low loads on the system is to avoid oversizing the system. An oversized system is forced to spend most of its time operating at low load. While the fixed metering device has no mechanical means for adapting to load changes in the system, they can automatically adjust to the load or float with the load, just as compressors and evaporators do. For the average comfort air conditioning system of around 3 tons cooling capacity or less, the entire system floats with the load well enough to operate in a stable manner without the need for sophisticated capacity control devices at the compressor, condenser, metering device, or evaporator. The system will automatically adjust its capacity up as load increases and down as load decreases to exactly match cooling load with capacity. Please consult the compressor and evaporators modules of this series to see how this principle works. When the load drops below the system's ability to automatically compensate, the system cycles off. The reason that the capacity of the fixed metering device floats downward with a reducing load is, at the evaporator, less refrigerant vapor is produced because less refrigerant is evaporated, since less heat is absorbed by the refrigerant in the coil. This condition occurs because less heat is available to be absorbed due to a lower cooling load. But at the compressor, the same volume of gas is removed from the evaporator per unit of time. Therefore, at the evaporator, the pressure becomes lower. Consequently, at the compressor, the suction pressure drops as well as the discharge pressure, which drops the pressure and saturation temperature at the condenser. Then, at the metering device, less pressure at its inlet, condensing pressure, produces less refrigerant flow through the metering device. This means less refrigerant capacity is available to the system. In addition to this change, which was started at the evaporator, The condensing pressure usually is reduced further because of the lower outdoor temperatures that accompany a cooling load reduction on most small comfort jobs. This fact simply adds to the automatic downward compensation in capacity. Conversely, the reverse of the above steps is true as the cooling load increases. At this time, stop tape and answer the skills check questions to this section in your workbook. There are 6 types of metering devices that mechanically adjust to cooling load changes. They differ in their mechanism and how they are controlled, but they all regulate refrigerant flow so that evaporator capacity matches the cooling load. Fixed metering devices are used on the vast majority of residential and room air conditioner products. The adjustable types are most often used on systems with variable load requirements. The hand-operated expansion valve illustrates the basic means by which refrigerant is metered through all the adjustable metering devices. It is a hand-operated needle valve. The rate of refrigerant flow through the valve is determined by 3 things: the size of the valve orifice or opening, the pressure difference across the orifice, and how far the valve is opened. An increase in any of these 3 factors will increase flow, while a decrease in any will reduce flow. To illustrate how this metering device matches capacity to system load, let's assume that we have an air conditioner cooling a small commercial building that uses an air-cooled condenser. It uses a hand expansion valve as the metering device. When the cooling load on the air conditioning system is low, say 50% of design load, the valve is manually adjusted to 1/2 open. This adjustment allows the refrigerant to enter the evaporator at a rate that produces slightly superheated gas leaving the evaporator. As the cooling load begins to rise, the valve needs to be opened a little more. If it is not, the evaporator will be starved, the suction pressure will drop, and superheat will be excessive. The result is that system efficiency and capacity will suffer. As the cooling load decreases, the valve must be closed a little. If it is not, the evaporator will be flooded with excess liquid refrigerant, causing the suction pressure to rise and liquid refrigerant to exit the evaporator. System performance will be poor, and the compressor may be damaged. The obvious disadvantage to the hand expansion valve is that it makes no automatic adjustments to match changes in the system cooling load. It must be opened or closed manually with each change in system load. An equipment operator has to be on hand at each change in system load. When automatic control is desired, or when the system load changes frequently, a different type of metering device is recommended. For these reasons, the hand expansion valve is seldom, if ever, used today. However, it was used in the past on large commercial or industrial jobs that had relatively stable loads and an operating engineer. The low-side float valve is a metering device that controls the flow by a float on the low-pressure side or low side of the metering valve. It maintains a constant level of liquid in the evaporator. As cooling load on the evaporator increases, more liquid is boiled away, and the liquid level in the evaporator and float chamber drops. As the float drops, it opens the metering orifice. This opening admits more liquid from the high-pressure side. As the load on the evaporator decreases, less liquid is boiled away and the liquid level increases. Thereby, the float rises, closing the orifice. The low-side float valve is normally designed and installed by the equipment manufacturer. Field selection and installation is the exception, not the rule. The low-side float may be installed directly in the evaporator, as just shown, or located in a separate float chamber, as shown here. When installed in a separate float chamber, both the top and bottom chambers must be connected to the evaporator, so that the liquid level is the same in both chambers at all times. Flooded evaporators normally make use of a low-side float. The low-side float is considered one of the best metering devices available for flooded evaporators, whether large or small. It gives excellent control, and its simplicity makes it very reliable. It can be used with any refrigerant. Like the low-side float valve, the high-side float valve modulates refrigerant flow to the evaporator based on liquid level. In this case, however, the float assembly is located on the high-pressure side of the metering device's orifice. It maintains a constant liquid refrigerant level either in the condenser or slightly downstream of it, as shown here. The pressure drop that the refrigerant undergoes after leaving the condenser is a result of the combined resistances to flow at 2 points. Pressure is first reduced as refrigerant flows through the orifice in the float valve. Further reduction occurs as the refrigerant passes through the pressure-reducing valve. Refrigerant vapor from the evaporator is transformed into a liquid in the condenser. The greater the evaporator cooling load, the more vapor enters the condenser. The result is that more vapor is condensed into liquid. As the liquid level climbs, it opens the metering valve, allowing more liquid to flow to the evaporator to match the amount that is evaporated. With less load, less liquid is evaporated, less vapor enters the condenser, and less will be condensed. The reduced liquid level causes the metering valve to move toward the closed position. When the compressor stops, the vapor from the evaporator is no longer sent to the condenser, and the liquid level in the high side float drops. This process causes the valve to close. It remains closed until the compressor starts and the condenser builds up enough liquid in the float chamber to open the metering valve. Both dry expansion evaporators, as just shown, and flooded evaporators, as shown here, use the high side float as a metering device. The most common application is in the flooded cooler of a centrifugal chiller. When it's used on a flooded evaporator, the liquid leaving the metering device enters the surge chamber rather than going directly into the evaporator coil. In the surge chamber, the flash gas is removed to the compressor suction along with gas evaporated within the coil. The liquid circulates through the coil. The high side float maintains a small fixed amount of liquid in the high side of the system. Consequently, the majority of the system refrigerant charge is always in the evaporator. This fact makes the system refrigerant charge critical. An overcharge will result in a flooded evaporator that will cause inadequate capacity and liquid flood back to the compressor. Undercharging will cause the float valve to act inconsistently, and the evaporator will be starved for refrigerant. An automatic expansion valve has a diaphragm which has a needle and seat below it and a spring with a tension-adjusting screw above it. A fine mesh strainer usually is included at the inlet to the valve as shown on this schematic diagram. It prevents any debris in the refrigerant from blocking the small passageway through the orifice. The automatic expansion valve is designed to maintain constant evaporator pressure. It does this by the interaction of the forces between evaporator pressure underneath the diaphragm and the spring pressure above it. A difference between the two causes the diaphragm to bend. This in turn moves the needle into or out of its seat. To see how this works, let's assume the adjusting spring is set so that the valve maintains 69 psig in the evaporator, 40 degrees Fahrenheit saturated evaporator temperature for R22. If the pressure in the evaporator is at 69 psig, the pressures below the diaphragm, evaporator pressure, and above the diaphragm, spring pressure, will be in equilibrium, and the needle will remain in its present position. The rate of refrigerant flow to the evaporator will remain unchanged. As the evaporator pressure falls below 69 psig, the spring pressure exceeds the evaporator pressure. This bends the diaphragm downward and opens the needle valves. Flow to the evaporator increases, which causes more of the evaporator's surface to be flooded. If adequate cooling load is available, more gas is evaporated, and the evaporator pressure returns to 69 psig. Again, the spring and evaporator pressures are back in equilibrium. If the evaporator pressure rises above 69 psig, the evaporator pressure overcomes the spring pressure. This bends the diaphragm upward and closes the needle valve. Refrigerant flow to the evaporator decreases, and less of its surface is flooded. Less refrigerant gas is evaporated, and the evaporator pressure returns to 69 psig. This action brings the spring and evaporator pressures back into balance. When the compressor cycles off, there will be some liquid refrigerant remaining in the evaporator that continues to boil, thus producing vapor. Since the compressor cannot remove this vapor when it's off, the evaporator pressure climbs above the spring pressure and forces the valve closed. The valve will remain closed throughout the off cycle. When the compressor cycles back on, the evaporator pressure quickly drops, allowing the needle valve to open and liquid refrigerant to flow to the evaporator to satisfy the cooling load. A disadvantage of the automatic expansion valve is that it's designed to respond to evaporator pressure instead of cooling load, or the superheat of the refrigerant as it leaves the evaporator. The result is that the refrigerant condition leaving the evaporator can become unacceptable under certain load situations. For example, if the cooling load decreases, less liquid refrigerant will boil into vapor within the evaporator. This causes the evaporator pressure to fall, which opens the needle valve. As more refrigerant flows to the evaporator, more flooding of its surface occurs. If the load is adequate, enough liquid will be evaporated to increase the evaporator pressure once again, balancing its pressure with the valve's spring pressure. If not, liquid refrigerant will flow out the end of the evaporator. This liquid overflow presents a serious hazard to the compressor. If, on the other hand, the load increases, more liquid refrigerant will boil into a vapor, increasing the evaporator pressure. This will move the needle valve toward the closed position and send less refrigerant to the evaporator. Less refrigerant means less boiling and lower evaporator pressure. As this happens, the valve returns to equilibrium. Less of the evaporator is flooded, and the refrigerant within it becomes more superheated. Evaporator cooling capacity is likely to become inadequate for the job, and the refrigerant leaving the evaporator may become excessively superheated. This may cause compressor overheating, which can result in high compressor discharge temperatures and pressures, oil breakdown, carbonization of valves, and poor efficiency. For these reasons, the automatic expansion valve is used on small capacity equipment with relatively constant loads. Examples include domestic refrigerators and freezers and small retail freezer cabinets. At this time, stop tape and answer the skills check questions to this section in your workbook. Like the automatic expansion valve, the thermostatic expansion valve, often abbreviated TXV, has a diaphragm with a needle and seat below it. It differs, however, because the adjustment spring is below the diaphragm rather than above it. The pressure exerted on the underside of the diaphragm is a combination of evaporator and spring pressures. The pressure on top of the diaphragm comes from a small cylinder called the remote sensing bulb or feeler bulb. This bulb is charged with refrigerant or another suitable chemical, which increases the pressure on top of the bellows as the temperature of the refrigerant pipe to which it's firmly connected increases. A fine mesh strainer usually is included at the inlet of the valve to prevent the valve from becoming plugged with debris that might be circulated with the refrigerant. To see how the TXV works, let's assume the adjusting spring is set to maintain 10 degrees Fahrenheit superheat at the remote sensing bulb location, the outlet of the evaporator. This is normal. Most valves come from the factory set for between 7 degrees Fahrenheit and 10 degrees Fahrenheit superheat. As long as the superheat measured at the sensing bulb matches that for which the adjustment spring is set, the diaphragm remains horizontal. It moves neither up nor down. The cooling capacity produced by refrigerant flow through the valve and through the evaporator are in equilibrium with the cooling load. The needle stays in its preset position. The combined pressures of the evaporator and spring below the diaphragm are equal to the pressure from the sensing bulb above it. If the superheat falls below 10 degrees Fahrenheit, however, the temperature of the refrigerant leaving the evaporator drops. This is sensed through the suction line by the remote sensing bulb. The saturated refrigerant temperature and pressure within the bulb drop. This sends a reduced pressure to the top side of the diaphragm. The combined force of the spring and evaporator pressures below the diaphragm now exceeds that from the sensing bulb above it, and the diaphragm bends upward. The needle moves toward the closed position, which allows less refrigerant to enter the evaporator. The reduced refrigerant flow increases the superheat, thus returning the system to equilibrium at 10 degrees Fahrenheit superheat. If the superheat rises above 10 degrees Fahrenheit, the saturation temperature and pressure of the refrigerant within the remote sensing bulb rise. This sends increased pressure to the top side of the diaphragm. The combined pressure of the evaporator and the spring below the diaphragm is now less than the pressure above it. The diaphragm bends downward, moving the needle toward the open position. This action allows more refrigerant to enter the evaporator. As more refrigerant enters the evaporator, the amount of superheat per pound of refrigerant decreases the system, then returns to equilibrium at 10 degrees Fahrenheit superheat. Now let's look at the actual pressures within the valve. We assume the system is charged with R22 and the adjustment spring is set for 15 psig, which matches 10 degrees Fahrenheit superheat for R22 at 40 degrees Fahrenheit saturation temperature. At equilibrium, the system cooling load matches capacity. The flow of refrigerant into the evaporator is just right to produce 10 degrees Fahrenheit superheat in the refrigerant gas at the remote sensing bulb location. For all practical purposes, the actual gas temperature in the suction line at the remote sensing bulb location matches the saturation temperature of the liquid vapor mixture within the sensing bulb, the tube connected to it, and the top of the diaphragm in the thermostatic expansion valve. This will be true, however, only if the sensing bulb is firmly clamped to a clean, straight section of the suction line near the evaporator outlet. The sensing bulb is designed to sense refrigerant gas temperature. It should not be located on the bottom of the suction line or other places where it will measure the temperature of liquid refrigerant should it accidentally enter the suction line. Once installed, it should be wrapped with waterproof, usually closed cell insulation, right along with the suction line. The insulation should extend at least 1 foot beyond the bulb in each direction. Always consult the equipment installation instructions for the correct location of the bulb. Here we have assumed that the evaporator pressure is 69 psig. This matches a saturation temperature of 40 degrees Fahrenheit. Since gas is superheated 10 degrees Fahrenheit, the actual gas temperature in the suction line at equilibrium is 50 degrees Fahrenheit. We have assumed that the refrigerant in the bulb is R22. For many comfort applications, however, a different refrigerant or even another type of chemical is used. Such valves are said to be cross-charged valves. Cross-charged valves are also used on commercial work where a constant superheat is not mandatory. At 50 degrees Fahrenheit, the saturation temperature within the bulb, the pressure is about 84 psig. This is the pressure exerted on top of the diaphragm. Below the diaphragm is the spring pressure, 15 psig, plus the evaporator pressure. At 40 degrees Fahrenheit saturation temperature, the evaporator pressure is about 69 psig. The combination of spring plus evaporator pressure below the diaphragm is 15 plus 69, which equals 84 psig. This matches exactly the pressure above the diaphragm, so it's bent neither up nor down and the needle stays right where it is. As cooling load decreases, but the same needle position is maintained, the refrigerant entering the evaporator will be superheated less. If the superheat drops to 4 degrees, the actual superheated gas temperature in the suction line at the sensing bulb will be 44 degrees Fahrenheit. Within the sensing bulb, a 44 degree Fahrenheit saturation temperature will produce a pressure of about 74.5 psig above the diaphragm. The pressure below it is still 15 psig spring plus 69 psig evaporator, which equals 84 psig. This pressure difference will cause the diaphragm to bend upward, moving the needle toward the closed position. This situation will continue until 10 degrees Fahrenheit superheat is once again attained in the suction line at the bulb location, returning the pressure above the diaphragm to 84 psig. As cooling load increases but the needle stays in its equilibrium position, the refrigerant entering the evaporator is superheated more. If the superheat rises to 16 degrees Fahrenheit, the actual gas temperature in the suction line at the sensing bulb will be 56 degrees Fahrenheit. Within the sensing bulb, a 56 degree Fahrenheit saturation temperature yields a pressure of about 94.3 psig. So, above the diaphragm, we have 94.3 psig, while below it we still have 84 psig. In this case, the diaphragm bends downward, and the needle moves toward the open position. The diaphragm will be flexed downward until 10 degrees Fahrenheit superheat is once again restored in the suction line at the sensing bulb location. This action returns the pressure above the diaphragm to 84 psig. Superheat at the evaporator outlet is an important measurement to have when troubleshooting a system or when adjusting the superheat on a thermostatic expansion valve. On most systems, the easiest way to measure superheat is to take one pressure reading and one temperature reading from the system as it operates. First, take a pressure reading at the suction service valve of the compressor. To get the saturation temperature which matches this pressure, check the reading on your service gauge set or on a refrigerant card or chart. Even though the reading is not taken right at the evaporator outlet, it will be approximately correct, especially if you are working on a packaged system. Now take a temperature measurement at the top of the suction line, right near the evaporator outlet, using an electronic temperature probe. The difference between the actual temperature and the saturation temperature is the superheat temperature. For split systems, you can improve the accuracy of your estimate by assuming that the saturation temperature at the evaporator outlet is about 1.5 degrees Fahrenheit above the saturation temperature at the compressor service valve. When adjusting the superheat on a thermostatic expansion valve, turn it counterclockwise. This usually reduces the superheat. Clockwise rotation increases superheat. Never adjust more than one turn at a time. Take superheat readings after each turn. Be patient. The system may take as long as 30 minutes to show the final results of one adjustment of the superheat screw. The thermostatic expansion valves shown previously are referred to as internally equalized valves because the evaporator pressure on the bottom of the diaphragm is internal to the valve. This pressure is the pressure at the evaporator inlet. Since there is resistance to flow as the refrigerant moves through the evaporator, the pressure at its outlet is always lower than at its inlet. This means that the saturation temperature at the evaporator outlet also will be lower than at its inlet. When evaporator pressure drop becomes significant, it becomes difficult to maintain the desired superheat temperature. Consider this situation. The pressure at the evaporator inlet is 69 psig. This matches a saturation temperature of 40 degrees Fahrenheit. If the coil had no refrigerant pressure drop, as we previously assumed, the valve would nicely maintain 10 degrees Fahrenheit superheat at its outlet. If there is a 10 psi drop in refrigerant pressure through the coil, however, the real superheat is not a 10 degree Fahrenheit. The 50 degree Fahrenheit refrigerant gas is superheated 10 degrees Fahrenheit when measured by the evaporator pressure at the coil inlet. The coil inlet is also within the valve. The problem is that the actual superheat must be measured based on the pressure where the superheat is sensed. At the remote sensing bulb, the pressure is 69 psig minus 10 psig, which equals 59 psig. The saturation temperature that matches this pressure is about 33 degrees Fahrenheit. Therefore, a 50 degree Fahrenheit actual gas temperature in the bulb location represents 17 degrees Fahrenheit superheat, that is, 50 degrees Fahrenheit minus 33 degrees Fahrenheit, not 10 degrees Fahrenheit as originally assumed. This means that too much of the coil is being used to superheat the refrigerant. This causes the evaporator's operation to become inefficient and perhaps short of cooling capacity. The externally equalized valve seals off the evaporator inlet from the bottom of the diaphragm and pipes in evaporator outlet pressure. Pressure and temperature are sensed in the same location by using the external equalizer line and sensing bulb respectively. This design allows superheat to be accurately maintained regardless of the pressure drop through the evaporator. This design also permits use of the entire evaporator surface, thus improving its heat transfer efficiency. The equalizer normally penetrates the suction line 6 or 8 inches downstream from the sensing bulb, unless the manufacturer's instructions indicate otherwise. Externally equalized valves are used on virtually all evaporators that are fed by a refrigerant distributor. Small capacity products with low evaporator pressure drops use an internally equalized valve. When in doubt, it never hurts to use an externally equalized valve. As we have shown, the conventional thermostatic expansion valve uses a remote sensing bulb that always has some liquid refrigerant in it. This may cause problems during the off cycle as well as at system startup, especially for air conditioning applications. When a compressor cycles off, the liquid refrigerant remaining in the evaporator continues to boil for a time. If the compressor doesn't remove the vapor produced by this evaporation, the pressure within the evaporator quickly rises. It will stabilize at the pressure that matches the temperature of the air surrounding the evaporator. For example, assume the air surrounding the coil is 80 degrees Fahrenheit. The pressure matching 80 degrees Fahrenheit saturation temperature for R22 is 143.6 psig. This pressure is exerted through the external equalizer line on the bottom of the diaphragm. Assuming the sensing bulb is also exposed to 80 degree Fahrenheit air, the same pressure is exerted on top of the diaphragm. Since the gas pressures above and below the diaphragm are equal, the spring pressure bends the diaphragm upward. This forces the valve closed. When the compressor starts, the evaporator sends refrigerant vapor at 80 degrees Fahrenheit saturated suction temperature into the compressor. This continues for a period of time before the new liquid flowing into the evaporator brings the temperature down to a normal range of about 30 degrees Fahrenheit to 50 degrees Fahrenheit for comfort air conditioning work. The high suction temperature causes excess compressor power consumption, which will cause compressor motor overload. If compressor motor overload continues, it also will cause compressor damage due to high discharge temperatures. Another complication encountered at startup results from the fact that the remote sensing bulb pressure is not limited. It can climb as high as the air temperature around it permits. For example, in the previous case, the 80 degree Fahrenheit air surrounding the sensing bulb placed a 143.6 psig force above the diaphragm. When the compressor cycles back on, the evaporator pressure below the diaphragm is quickly reduced. Consequently, the bulb pressure above the diaphragm becomes a powerful opening force that tends to slam the valve fully open. As a result, liquid refrigerant is likely to flood the compressor before the valve regains control. Due to these difficulties and others, virtually all air conditioning systems using thermostatic expansion valves limit the maximum pressure that can develop in the evaporator. They do so by using pressure-limiting valves, also called a maximum operating pressure valve, or simply MOP valves. Some styles limit the maximum operating pressure in the evaporator by mechanical means, such as a spring. Others achieve the same result by using a limited refrigerant charge in the sensing bulb of the valve. In the valves shown so far, there has been sufficient refrigerant vapor in the sensing bulb, its tubing, and the area in the valve above the diaphragm that there always is some liquid refrigerant present in the bulb. For this reason, the term liquid charged valve is sometimes used. The limited charge valve, on the other hand, is an MOP valve that has enough refrigerant liquid present below the pre-selected maximum operating pressure and temperature that goes with it. Above that pressure and temperature, the refrigerant in the bulb, tube, and in the space above the diaphragm is all vapor. Increases in the temperature of a vapor produce only a slight increase in pressure. For all practical purposes, when a gas-charged valve is used, the pressure on top of the diaphragm stops increasing when the temperature at the sensing bulb reaches a certain limit. This solves the problems of liquid residual at compressor shutdown and startup. This electronic expansion valve is activated by an electronically controlled stepper motor. The motor shaft moves in and out in tiny steps. When the sleeve attached to the shaft moves upward, it exposes more metering slots. This increases refrigerant flow to the evaporator. When it moves downward, it covers the slots, thus reducing flow and cooling capacity. One manufacturer uses this type of valve on reciprocating package chillers from 280 tons of cooling capacity instead of the conventional thermostatic expansion valve normally found on this sort of equipment. Like the TXV, this type of valve is designed to maintain constant superheat. The stepper motor gets its signal from an electronic control panel that's attached to an electronic sensor that measures refrigerant superheat. Since it is controlled independently of pressure, this valve is able to provide safe startup, safe shutdown, stable operation, and high energy efficiency through its full range of operating conditions. As electronic control systems increase in popularity, we can expect to see electronically controlled valves on more and more systems. When flow through the thermostatic expansion valve drops below 30%, the valve will not hold a constant setting. It loses its ability to maintain a constant superheat, and it begins a process called hunting. When hunting, the valve alternately overfeeds the evaporator and then underfeeds the evaporator. You can identify hunting by taking superheat readings with a temperature probe. The readings must be taken on the suction line near the TXV sensing bulb for a period of time. One reading will not give a true picture. The reading must be done over a longer period of time. If superheat varies in a repetitive pattern from too high to too low, hunting may be the problem. A smaller thermostatic expansion valve will be required to remedy the problem, or refrigerant flow to the valve needs to be shut off when the compressor drops to the capacity level. Even with the best metering device, the evaporator, and therefore the system, will not function properly if the liquid and gas mixture leaving the metering device is not properly distributed to the evaporator circuits. Systems with a very small capacity may use a single refrigerant pathway or circuit through the evaporator. In these cases, the metering device is installed as close to the evaporator inlet as possible, and distribution of refrigerant presents no problem. The vast majority of systems, however, use evaporators with multiple refrigerant circuits, similar to the one shown here. This one has 5 circuits. Each one must receive the proper amount, usually an equal amount of the liquid and gas refrigerant mixture as it leaves the metering device. The feeder tubes are usually equal lengths of copper or aluminum. Their outside diameter varies from 5/32 to 3/8 of an inch, depending upon the capacity of the evaporator and the number of circuits involved. The distributor is designed to feed equal quantities of the refrigerant mixture to each circuit. The distributor has from 2 to 40 outlets, depending on the size of the evaporator. There is one distributor per metering device. However, there may be more than one metering device per evaporator, especially for systems above 50 tons of capacity. Some distributors, like this one, have a thick, flat washer inside. It's called a nozzle. Its purpose is to provide a pressure drop which thoroughly mixes the refrigerant liquid and gas so that each circuit gets an equal mixture of gas and liquid. Other distributors rely upon the internal design of the distributor to evenly mix gas and liquid. Both distributor nozzles and thermostatic expansion valves have low load limitations. They function poorly below these limits. If either of these devices is incorporated on packaged factory-assembled equipment, there should not be any low-load problems. This statement assumes all other components are functioning properly. However, if the nozzle or valve is selected elsewhere, it's a potential source of service trouble at low load. Oversizing either component or controlling capacity steps improperly can cause problems. Oversizing is the most common source of these problems. The low load limit for most nozzles is about 50% of its maximum capacity. For most thermostatic expansion valves, the minimum load is about 30% of its maximum. When the flow through a nozzle drops below 50%, the gas and liquid refrigerant are not equally mixed. Gas goes to the top circuits, while liquid goes to the bottom ones. The superheat from the top circuits is excessive, while liquid refrigerant floods back to the compressor from the lower circuits. An easy way to spot this malfunction is to check for higher temperatures at the tubes on the top circuits of the evaporator and lower temperatures at the bottom tubes. The solution for this problem is to replace the nozzle with the next smaller size, or to rearrange the controls to shut off one section of the evaporator before the low limit is exceeded. When flow through the thermostatic expansion valve drops below 30%, the valve will not hold a constant setting. It loses its ability to maintain a constant superheat, and it begins a process called hunting. When hunting, the valve alternately overfeeds the evaporator and then underfeeds the evaporator. You can identify hunting by taking superheat readings with a temperature probe. The readings must be taken on the suction line near the TXV sensing bulb for a period of time. One reading will not give a true picture. The reading must be done over a longer period of time. If superheat varies in a repetitive pattern from too high to too low, hunting may be the problem. A smaller thermostatic expansion valve will be required to remedy the problem, or refrigerant flow to the valve needs to be shut off when the compressor drops to the capacity level. Some small capacity systems have only a few refrigerant circuits in the evaporator. The need for a distributor can be eliminated in such cases by using a multi-port, multi-outlet TXV. The example shown in this schematic diagram is an internally equalized double-port valve. The distribution of refrigerant is accomplished within such valves, eliminating the need for a separate distributor. Unattended problems in the metering device are likely to result in an eventual compressor failure. If the service technician replaces the compressor without identifying and correcting the root cause, the compressor is sure to fail again. Repeat compressor failures are a major problem in the air conditioning industry. They result in unhappy consumers as well as tremendous unnecessary cost in labor and parts for dealers and manufacturers. One of the things you should strive to get out of the GTAC program is a thorough understanding of the causes and symptoms of compressor failure and how each component can contribute to such failures. The ways in which evaporators can contribute to compressor failure are summarized here. Also, a troubleshooting guide that concisely highlights metering device problems and their symptoms causes is provided at the end of this module. The controls that regulate electrical and refrigerant flow through an air conditioning system determine whether or not the system accomplishes its purpose in a safe and efficient way. In the next module, we will train you in the function and placement of the more common controls used on air conditioning systems. Now is a good time to take stock of what's been gained during your study of this module. Review the skills shown on the Student Skills Inventory sheet located at the back of this booklet. It should encourage you to see that you have many more of these skills now than when you first began this module. There probably are some areas that need additional review. Repetition is a normal part of the learning process. Why not circle those skills that need additional work and go back to review those sections once again, answering the skills check questions that apply. At this time, stop tape and answer the skills check questions to this section in your workbook.